good day to all of you. Today we are going to learn the triple integral in Cartesian coordinates. Recall that volume of a solid above the region R, for example, the region R here, this triangle, on the xy plane. Volume of a solid above the region R and below the surface z equal to fxy. For this case, the z equal to fxy is 3 minus x minus y. You have the top surface is z equal to fxy and the bottom surface is your region R, which is on the xy plane, or z equal to 0. To find the volume here using double integral, the v is equal to the double integral, the fxy dy dx or dx dy. Depend on the shape of your region R. And then if you want to find the same volume, in the top surface is z equal to 3 minus x minus y, and the bottom surface is on xy plane, or z equal to 0. In triple integral, is actually, if you see, this one is parallel with z axis, then we integrate respect to z first. So integrate dz. This is lower limit of z because the bottom surface is on xy plane, so it's z equal to 0. Upper surface is given by 3 minus x minus y, so this is the upper surface. Then you integrate respect to z first. Later on, the dy dx here is same with the double integral. Then if you evaluate, the triple integral, we have to evaluate start from the inner integral. So mean you integrate one respect to z where y and x are constant. Integrate one respect to z, you have z. Substitute the limit from 0 to a function of fxy, then you get back fxy. You notice that in this step, this is actually equivalent back to what you have done in double integral. So the difference with triple integral and double integral here, double integral is more flexible, where the lower limit or the lower surface not necessary z equal to 0. It will be more flexible. It's more flexible, And then, however, if using double integral, your bottom surface is always the region R is always on the xy plane, on the xy plane for the orientation of the dy dx or dx dy. So in triple integral, it's not necessary. The lower limit is z. Z equal to 0 can be any bottom surface. Before we go for further how to evaluate the triple integral, define here. In general, volume of a solid G bounded by the top surface z equal to f2xy, the top surface, let's say, is z equal to f2xy, and bottom surface, let z equal to f1xy, and its projection is region R, is given by, the region R is on here, this one. If the solid is parallel with z, then the region R will be on the xy plane. The region R is on xy plane. Then it's given by this triple integral. V is a volume. Is triple integral 1 dv, over the solid G. Let's say because here the shape of this solid G is bounded by top and bottom surface, then we integrate respect to z first. So the lower limit here, you notice, compared to the second double integral, lower surface of the f1 xy not necessarily equal to 0, can be flexible any surface. And this is a top surface. So dA can either be dy dx or dx dy. Look at this region here. Let's say this is a bottom surface given by z equal to f1 xy, top surface is f2 xy, and its projection, when you press this solid Okay, this one is I took the photo from another book. They use a G instead. They use D instead of I use G. Yeah? When you press this solid G, the projection scale of the region R will be on XY plane, and we notice that this region R is actually bounded by bottom curve, which is y equal to g1x, and the top curve, which is y equal to g2x. That's why limit of y will be from the bottom curve, y equal to g1x until y equal to g2x. You sum it vertically. Okay, notice this is the y-axis, x-axis is here. And you sum this vertical bar in your region R, okay, from left to right, which is x equal to a until x equal to b. So this is one of the orientations of the triple integral. Actually, total we have 6 orientations, means 6 order. Okay, and then before we start the example, let's consider you have a unit cube here. You have a unit cube, okay. Remember, this is the x-axis, this is the y, vertical is the z-axis. Okay, this is one unit cube here. Okay, this is dy, dx, dz. Hence, okay, the volume of the unit cube will be, take the dz multiply dy multiply dx. Okay, and if you sum this unit cube vertically in parallel to the z-axis, you sum it vertically or parallel to the z-axis, the shaded area here is actually we do the triple integral dz from the we do the inner integral. We integrate dz from triple integral. Okay, later on, if we sum it parallel, we sum these two cubes here. Later we sum these two cubes parallel with the y-axis. It's actually what we did is here. Alright, guys, we already evaluate the integrate dz. Later on, we integrate respect to y from the triple integral. Lastly, we sum it parallel to the x-axis. Then is what we have here. Triple integral dz dy dx. So this is idea of the volume as a triple integral. Okay, example 1. Find the volume of the solid G which is bounded above by the coordinate plane and the plane actually bounded above by this plane, bounded above by the plane, okay, tetrahedral plane x plus 2y plus 3z equal to 6, okay, and the coordinate plane in the first octant means x positive, y positive, z positive. Okay, so first of all, okay, we look at this tetrahedron plane x plus 2y plus 3z equal to 6. This one. Okay, how I get the x-intercept is 6, y is 3, z is 2. How I get it? From here. Okay, the surface x plus 2y plus 3z equal to 6. To get the x-intercept, you let y 0, z 0. That's why you get x equal to 6. Okay, and then, okay, to get the y-intercept, you let x 0, z 0, then 2y equal to 6, hence y equal to 3. Okay, lastly, to get the z-intercept, you let x and y 0, 3z equal to 6, and z will be equal to 2. So this is a tetrahedron surface. Okay, mean the upper surface is bounded by this tetrahedron, x plus 2y plus 3z equal to 6, and the coordinate planes is actually, here you have the zx plane, this is zy plane, bottom is your xy plane, and is in the first octant, so mean x positive, y positive, z positive. Okay, then we want to find the volume bounded above by this tetrahedron in this three coordinate plane. So actually we have six ways to solve it. Okay, first of all, if you view this surface which is parallel with z axis, then okay, you integrate with respect to z first, and if you view it parallel with z axis, then you press it, the region R will be on the xy plane. So I said here, solve by xy plane projection means okay, you view the solid parallel with your z axis, then you integrate with respect to dz first. That's what the previous explanation. When you sum the unit cube vertically is actually you integrate with respect to z first. Okay, and then to integrate with respect to z, you need the lower limit of z and upper limit of z from the surface, the tetrahedron surface. Make your z as a title, then you get z equal to 6 minus x minus 2y divided by 3. So this is the upper limit, means upper surface become the upper limit. Okay, and you want to find the volume of this tetrahedron bounded by three coordinate planes, right? So if you view this surface as a top surface, its projections will be the on the xy plane of z equal to 0. So z equal to 0 is the lower limit, okay, and z equal to 6 minus x minus 2y over 3 is the upper limit of your z. Okay, so you have here this one. So z0, okay, up to z equal to 6 minus x minus 2y over 3. Integrate respect to z first. Okay, after you integrate respect to z, okay, you can either integrate use dy dx or dx dy. Okay, depends on the region R. Okay, the region R, we get this triangle. Okay, the shaded triangle. And then how I get this equation? Okay, from the tetrahedron equations, x plus 2y plus 3z equal to 6. Because your region R is on xy plane, hence the z is 0. That's why you have x plus 2y equal to 6. Okay, x plus 2y equal to 6. Here, you either your a there, dy dx or dx dy. Okay, if I use the dx dy, is actually, I will sum up the region here vertically. Okay, and this vertical bar touch y-axis or y equal to 0. This is y equal to 0. And this is a lower curve. Your upper curve, better you use this orientation, easy to do the calculation. Mean y is 6 minus 2x over 2, rather than you use y equal to 3. So this one is to be y minus 6 minus x over 2. Had 2 mistake. Okay? 6 minus x over 2. And then we'll sum this vertical bar from left, which is x0 until x equals 6. Where is it? x0 until x equals 6. And then y from 0 until y equal to 6 minus x over 2. Yeah. 6 minus x, back 4. This one is a back 4. Okay. So that's how we get the limits. Limit for z is the bottom surface up to the top surface. Limit for y is from the dy is from the region R. This is a lower curve up to the upper curve. X, okay, from left to right. Okay, after that, okay, you just need to integrate. Okay, first of all, integrate respect to z. Integrate 1 respect to z, while y and x are constant. You will get z. Okay, plug in the limit. Okay, lower limit is 0, upper limit is 6 minus x minus 2y over 3. So you get 6 minus x minus 2y over 3 plus minus, okay, the lower limit is 0. So minus 0. Okay, later on, okay, you can, this is divide by 3, you can factor out, become 1 over 3, and then you integrate 6 minus x minus 2y respect to y. When you integrate respect to y, 6 minus x, this one is actually a constant. Because when integrate respect to y, x is constant. So 6 minus x is constant. That's why you have a constant multiplied with y. So integrate negative 2y respect to y. You have negative 2y squared divided by 2. That's why you get negative y squared. Then plug in the limit from 0 to 6 minus x over 2. Okay, and then, so remember you integrate respect to y, then plug in into variable y. So 6 minus x times 6 minus x over 2 minus, this is the upper limit, 6 minus x over 2 squared. Okay, lower limit is 0, so it totally is just minus 0. Okay. And then you simplify before you integrate respect to x. So you have 6 minus x times 6 minus x. So you have half of 6 minus x squared. Okay, and then this is minus. So this is 6 minus x squared and then 2 squared. So it's minus 1 over 4, 6 minus x squared. Then you will get, okay, half of 6 minus x squared minus 1/4 of 6 minus x squared. Total you have 1/4 6 minus x squared. Okay, and then you factor out 1/4, you have 1 over 12. Then integrate 6 minus x squared. You can use the substitution techniques. U equal to 6 minus x. And then the du is negative dx, and dx will be negative du. Hence, the integral of 6 minus x squared dx will be equal to, when you replace 6 minus x by u, so you have, okay, u squared, dx is negative du, integrate u squared respect to u, you have u cubed over 3, negative is come from, okay, dx is equal to negative du. So replace back your u is 6 minus x, oh, sorry, again, type 4. This is cube. Okay, so you have negative 1 over 6 minus x cubed. And then plug in the upper limit. Evaluate it, you get the answer is 6. Okay. In case you forgot how to integrate here, you may use your scientific calculator. In the mode calculate, let's say you want to integrate here, this 6, okay, this one already 1 over 12. Okay, I just want to show you how you use a scientific calculator to integrate 6 minus x squared. Here. Six minus alpha x. This make it bigger. 6 minus x squared. Minus x squared, and then you are going to integrate from 0 to 6. 0 to 6. 72, and then we have actually here divide by 12. So the answer is 6. This is using scientific calculator in case you forgot, okay, how to integrate. Okay. This is using substitution technique, or you may use your scientific calculator, okay, to integrate 6 minus x squared dx from 0 to 6. You get just now the answer is 72, and then you, okay, because we have here 1/12, then divide by 12, you get answer is 6. Okay, here I have shown, okay, how to solve this tetrahedron, okay, which is bounded by coordinate plane. and I assume that I treat that the volume bounded by the tetrahedron is actually parallel with the z-axis. So I integrate respect to z first, and then the region R, okay, I prefer to use the vertical bar to sum it. That's why I use dy dx. Okay, you may also try to change it to dx dy. I mean, you integrate respect to x first. Then you will sum it. Okay, you will sum it using the horizontal bar. Okay, in the dy dx, you may change it to dx dy. Hence, the horizontal bar touch the left curve. This one y-axis, which is x equal to 0. X equal 0. Okay, until this curve, okay, is actually from x plus 2y equal to 6, then the x will be equal to 6 minus 2y. If you want to use dx dy, then lower limit of x will be your left curve, which is x equals 0, up to x, okay, the right curve, which is x equal to 6 minus 2y. And you're going to sum this horizontal bar from the bottom of your region R, which is y equals 0, until this one y equal 3. Mean you will sum it, okay, by horizontal bar. Hence, okay, you have another, okay, orientation where you change dy dx to dx dy. Then limit of y, okay, from 0 to 3. Y here, from 0 to 3, limit of x with 0 up to x equal to 6 minus 2y. Okay. Besides that, if you view, okay, this solid is actually parallel with your y-axis, then its projections will be on, okay, I mean parallel with the y-axis. Then you integrate respect to y first. Integrate, if you view it, okay, parallel with the y-axis, you integrate with, okay, y first, and the projections will be on z-x plane here. Here, z-x plane or x-x plane. When you integrate respect to y first, okay, mean dy first, is actually we view, okay, your solid is parallel with the y-axis. In y-axis is here. If you view it parallel with the y-axis, okay, when you press it, okay, press along the y-axis, the projections will be on xz plane, So in this case, you will integrate respect to, okay, y first, and the projection will be on your, okay, zx plane. So if you integrate respect to y first, you have to, okay, get the, okay, y as a title from the tetrahedron equations here. So where the y will be 6 minus x minus 3z divided by 2. So this will be the upper limit of the y, where, okay, the lower limit will be the projection, okay, of the region R, which is on xz plane or y equal to 0. So this is y0 is the lower limit. This will be the upper limit. We put it here. Y0 until y equal to 6 minus x minus 3z over 2. Okay, and against the region R, I will solve it using vertical bar. Okay, I prefer the vertical bar. Okay, how I get the equation x plus 3z equal to 6. Similarly, if we integrate respect to y first, the projection is on xz plane, where y equal to 0. When you make it 0, that's why you have the x plus 3z equal to 6. And then if you want to solve it using, okay, vertical bar, means you sum the area of the region R using vertical bar, and this vertical bar touch the z-axis, which is z equal to 0, until the upper, okay, curve, which is x plus 3z equal to 6, or z equal to 6 minus x over 3. So this is upper limit, this will be the lower limit. In z0 until z equal to 6 minus x over 3. And against your sums the vertical bar from left, which is x equal to 0 until the right side, which is x equal to 6. x0 until x equal to 6. Okay, and then the rest, how to integrate, will be similar with previous orientation. Okay, and you can go back to try to change it to another way, which is dx dz. Okay. Okay, so total you have 4 orientation already. The 5th orientation is if you solve it by projection on yz plane, okay, or you integrate respect to x first, mean you view the solid is actually parallel with the x-axis. Parallel with x-axis, this is a solid. You view it parallel with x-axis, so you press it, your projection will be on zy plane. Okay, and then how you get the projection R here on zy plane, you let x equal to 0. That's why you get 2y plus 3z equal to 6. Okay, and then before that, if you integrate respect to x first, and then you need the limit of x, and then the upper limit of x is actually obtained from the upper surface x plus 2y plus 3z equal to 6. Okay, you want to integrate respect to x, you must have x as a title. So x here will be 6 minus 2y minus 3z, which is the upper limit of x. Okay, the projection is on yz plane or zy plane, or x equal to 0, which is the lower limit. So x0 until x equal to 6 minus 2y minus 3z will be the upper limit of your x. Here. So x0 until x equal to 6 minus 2y minus 3z. And then, the region R, again, I solve it using vertical bar. Okay, the vertical bar touch, the z-axis, or z equal 0. So z equals 0. Okay, top curve is 2y plus 3z equal to 6, where you obtain it by letting x equal 0. Then z is 6 minus 2y over 3. Here. And you sum the vertical bar from left side, which is y0 until y equal to 3. So that one will be the same integration. So this is the 5th orientation, and dz dy here you may reverse it, become dy dz. So total we have 6 orientation to solve your triple integral. If you use dy dz, mean you use the horizontal bar. Okay, this is the first example. The second example, find the volume of the solid G, which is bounded above by the surface x plus 2y plus 3z equal to 6 and below by z equal to 1. Okay, compared to the previous example 1, now the bottom surface no longer on xy plane, but will be on the plane z equal to 1. Hence, this solid is actually bounded. We have the top surface, bottom surface in the first octant. Then will be easier. You integrate respect to z first, because it looks like it's bounded by top and bottom surface. So you integrate respect to z. So x plus 2y plus 3z equal to 6. Okay, solving for z, you have z equal to 6 minus x minus 2y divided by 3, which is upper limit of your z. Okay, lower limit, your lower limit, is z equal to 1. Okay, copy paste. Lower limit is actually z equal to 1. Different example 1. Now lower limit is z equal to 1. Upper limit is from tetrahedral equation. You solve z as a title. So integrate 1 dz. And then your region R, to get the region R, is actually, this is the region R here. Your region R. To get the region R, you have to solve the intersection of the z equal to 1 and x plus 2y plus 3z equal to 6. So you substitute here z is 1, hence you get the x plus 2y equal to 3, mean this smaller triangle. Compared to the previous example, where the region R is larger, where the z equal to 0. You see on xy plane, we have a larger region R. But this one on z equal to 1, we have a smaller triangle, which is x plus 2y equal to 3. So from x plus 2y equal to 3, if we want to solve it using dy dx, then solve y as a title. You have y equal to 3 minus x over 2. Here. And then to get the intercept, you notice here, when y0, x is 3. X is 3. Okay. And then when x0, y is 1.5. Compared to if your region R is on xy plane, the x-intercept is 6, okay, y-intercept is 3. So this one, when you solve that tetrahedron bounded by the bottom surface is z equal to 1, your region R will be smaller triangle. Okay, this one will be easy to see, smaller triangle. Okay, when we solve just now, this one, this is 3. This one is actually 1.5. 1.5. Okay. So you solve it using the vertical bar techniques, mean dy dx. So y, okay, touch the y-axis, which is y equal to 0. Y equal to 0. Okay, until this curve is actually from x plus 2y equal to 3 or y equal to 3 minus x over 2. 3 minus x over 2 and x from 0 to 3. Okay. Similarly, now we integrate 1 respect to z. We have z. Plug in the limit. We have 6 minus x minus 2y over 3 minus 1. Okay. I factor out 1/3. So we have 6 minus x minus 2y minus 3. Because I factor out 1/3 here. And similar with example 1 just now. We simplify first, 6 minus 3, we have 3, minus x minus 2y. Later on, we integrate respect to y, where the whole thing, 3 minus x will become constant. Then you have 3 minus x times y. So minus 2y integrate respect to y. You have minus 2y squared over 2 become minus y squared. Then we plug in the upper limit. So this is 3 minus x times 3 minus x over 2. So minus 3 minus x over 2 squared. Then because lower limit is 0, so minus 0 is nothing. And then you simplify it. 3 minus x, 3 minus x. So you got 3 minus x squared divided by 2. So this is 3 minus x, you squared it. And then don't forget 2 squared. Okay. 2 squared of 1/4. Simplify 1 over 2 minus 1 over 4, okay, of 3 minus x squared. Total you have 1/4, 3 minus x squared. So you factor out 1/4, you have 1/12. Okay, and then you integrate this one. It's either using your scientific calculator or substitution technique. You'll get 3 minus x cubed divided by negative 3. So you have negative 1 over 36. Okay, so total you factor out this thing. We plug in the upper limit. Okay, deduct by the lower limit. Okay, total you get, this one is 0. So minus 3 cubed. Simplify, we have 3 over 4. 3 over 4. This is the second example. Okay, the third example, find the volume of the solid G in the first octant, which is bounded by the plane y plus z equal to 4, cylinder y equal to x squared, xy plane, and yz plane. Okay. This one. We have the plane, okay, y plus z equal to 4, and we have the cylinder y equal to x squared, and then xy plane means z minimum is xy plane, so z equal to 0. Okay, yz plane give x equal to 0. This is the surface. You have the y, okay, cylinder y equal to x squared, okay, bounded by the xy plane, or your z equal to 0, and then also bounded by the yz plane, x equal to 0. So that's why your cylinder only, okay, half of the parabola cylinder, half only, because also bounded by zy plane, xy plane, zy plane. That's why only half of the, okay, parabola y equal to x squared. And then this is z plus y equal to 4. So the z-intercept and y-intercept is 4. From 4 here, just drag it parallel to your x-axis, and the curve plane y equal to 4 intercept with the curve y equal to x squared and x equal to 2. Because when y is 4, x is 2. Okay, the other side x equal to negative 2, because our solid is bounded by zy plane, xy plane. So this is a solid G. Okay, if you view this solid G parallel with z-axis, means, okay, bounded by this top surface, z plus y equal to 4. Okay, then if you want to integrate respect to z, means you view it parallel with your z-axis, then you have to make z as a title. So z will be equal to 4 minus y. Okay, bottom surface here, z equal 0. Okay, and you integrate respect to z first, z 0 until z equal to 4 minus y. Okay, and then your dA, this is actually the dA, is either you solve it using dy dx or dx dy. Okay, so your dA is actually the region bounded by your parabola y equal to x squared and y-axis, and then because y here the plane z plus y equal to 4 intercept at y equal to 4, so the region R is here. Make sure you get the correct region R, bounded by the parabola y equal to x squared. Okay, because your parabola is also bounded by zy plane, so y 0, then up to y equal to 4. So the region R here. So I will prefer to use the, okay, dy dx, the vertical bar. Then my y will be equal to x squared until y equal to 4. Y equal to 4. Right. This is y equal to x squared. And then you sum the vertical bar from left, which x0 until x equal to 2. If you use dx dy, then x0, here you have to make x become surd y. Later on, maybe it's difficult because you meet with the surd to integrate, maybe a little bit difficult. That's why I would prefer you use dy dx. So y from the lower curve, which is y equal x squared until y equal 4, x from 0 until x equal 2. integrate 1 respect to z. You get z, substitute the upper limit with the lower limit, you get 4 minus y. 4 minus y. Then later on, you integrate respect to y. So you have 4y minus y squared over 2. Where the limit of y from x squared until 4. So you plug in the upper limit here. So 4 times 4, 16. 4 squared 16 divided by 2 is 8. And then 16 minus 8, you have 8 here. Then you plug in the lower limit, lower limit. So 4 times minus with substitution of lower limit, minus 4x squared minus x squared and squared again, x power 4 over 2. Simplify. So minus 4x squared minus this plus x power 4 over 2. Until here, you may use a scientific calculator to integrate, or you can integrate manually. If you solve it by ZY plane, mean you integrate respect to x first. It's actually you view the solid parallel with the x-axis. So that we solid here. When you view this solid parallel with the x-axis, then you press it, because you view it parallel with x-axis, and then you press this solid, the projection they on ZY plane. So you see your projection is here, this triangle. This one. Then if you want to integrate respect to x first, you must have x as a title. So from the cylinder y equal to x squared, it gives you x equal to third y. So this will be upper limit of your x. Lower limit is on ZY plane of x equals 0. In your upper limit is this one, the cylinder, x equals third y. Lower limit is ZY plane, which is x equal 0. So x0 until x equal to third y. The projection is a triangle. Z plus y equal 4, or z equal to 4 minus y. This will be upper limit of your z. Lower limit is z equal 0. Z equal to 0. 0 until 4 minus y. And you sum the vertical bar from y0 until y equal 4. So integrate 1 respect to x, you get x. Put in the limit, you get third y, dz dy. And then you integrate third y respect to z, to where y is constant. So you have a so you get this one is third y times the z, where put in the limit z from 0 to 4 minus y. So you have 4 minus y times third y. So you have 4 third y minus y 3 over 2. You may use scientific calculator to integrate, or you can integrate manually. So integrate 4 third y is y power half. For integrations, integration you increase the power by 1. So y power 3 over 2 divided by 3 over 2. And then this is integrate y power 3 over 2 become y power 5 over 2 divided by 5 over 2. Plug in the upper limit and lower limit. Simplify it, you get this is answer 128 over 15. Or from here, you can straight away using your scientific calculator. Show you example. Just integrate 4 third. Of course, in scientific calculator you don't have cannot using the y for the integral. You can only use the x, x. And then minus. This is the alpha x, and then power 3 over 2. integrate from 0 to 4. It will take some time. Okay. .5333. You check it whether this one's same. 1, 2, 8, do that. 15. Same. 8.53. This one. 8.53. Same. So in exam, until this step, you can also use your scientific calculator to obtain the answer. Okay, the last example, find the mass of a solid in the first octant which is bounded by the cylinder y squared plus z squared equal to 1, the plane y equal to x, and x equal to 0, given that the density function is delta xyz equal to z. Okay, this is a solid. Okay, the cylinder y squared plus z squared equal to 1. Okay, in the first octant. Okay, and bounded by the plane y equal to x. Okay, y equal to x. And x equals 0 means that's why the cylinder is up to the zy plane, x0, and bounded by y equal to x. So this is the resultant solid G here. Okay, now we want to find is actually the density, the mass. Okay. Okay, the mass is given by the triple integral, the density function multiplied dV. Okay, in secondary school, you may learn the density. Okay, is a m, the mass divided by volume, or the mass is actually your density times V. Okay, this is if we have a constant density. Here we have a variable density. We don't use a rho because we use it in spherical coordinate later on. So you change the rho to the delta. So because the density is not constant but is function of x, y, z, that's why the mass of a solid G is given by triple integral, okay, density function dV, okay, for the solid G. Okay, now if you view this solid parallel with z, okay, axis, then you integrate respect to z first. Okay, since it's on the xy plane, right? Integration. First, because first octant. So, okay, the lower surface will be z0. Upper surface, you solve it from the y squared plus z squared equal to 1. It gives you z equal to cert 1 minus y squared. This is the upper surface, which is upper limit. Lower surface is on xy plane, or z equal to 0. So, z0, okay. Solving from the cylinder, okay, equation, you get z equal to cert 1 minus y squared because the cylinder is in the first octant only. And then to get the dA, you have a look at the projections. Okay, the projection is actually, you have here, this one, this is 1, this is 1, okay. Then y equal to x. When y is 1, x here is 1. So you have the triangle, okay. The region R is a triangle given here. When y is 1, x is 1. So you will solve your dA using the vertical bar, then you use integrate respect to y first. So lower limit of y is y equal x until upper limit y equal to 1. X until y equal to 1, and then x from 0 until 1. Okay, then you integrate z, dz, you have z squared over 2. Okay, plug in the limit, okay, here, square root and squared, that's why you left 1 minus y squared. Integrate respect to y. So integrate 1, you have y, so minus y cubed over 3. Put in the limit for the y is from y equal x until y equal to 1. Okay, course here, so you have 1 minus 1 third, 2 third, so minus, okay, this is a substitution of lower limit, so x minus x cubed over 3. Okay, lastly, you integrate respect to x, or use your calculator. You get the answer here is 1 over 8. Okay, if you view, okay, if you want to solve it by the zy plane projection, then you integrate respect to x first. Respect to x first. Okay, you can view this solid. You can easily see the zy plane projection. Then you integrate respect to x. Means the cylinder here, you view it parallel. It's actually y squared plus z squared equal to 1 without x variable. This cylinder is actually parallel with the x-axis. Parallel with x-axis. The projection is on zy plane. Then you can integrate respect to x first. Okay, you integrate respect to x. You need the x as a title. So here, they give you x equal to y. This will be upper limit. Okay, from here, y-axis is actually x equal 0. And the projection is from the quadrant of the circle. Quadrant of circle. We have z squared plus y squared equal to 1. Here, against this quadrant of circle, we solve it using, this is zy plane, dz dy. Okay, so what just now? X 0 until x equal to y. And then here, we have this one, z0. From here, make z as a title. Z is equal to third 1 minus y squared. And y from 0 until 1. Integrate z respect to x. Z is a constant. So factor out. So we integrate to get zx. Plug in the limit. So you have zy. Then you integrate respect to z, where the y is a constant. So you have a z squared over 2, y is here. Plug in the limit for the z from 0 to third 1 minus y squared. So you have 1 minus y squared, okay, here. Then you expand it. So y, you expand it here. So y minus y cubed. Lastly, you integrate respect to y. Put in the limit to get 1 over x. Okay, with this, okay, thank you for your attention.